Today we are chatting about motion, and it's physical science, grade 12, and we have a fantastic teacher named Tracy. She's got a fabulous laugh and she's going to take us through today's show, and it's going to go like this. So stay tuned. And Tracy, hi.
Hi, Indian.
How are you today?
Good, and you?
Okay, good. Tell us what you're going to take us through today.
Well, today what we're going to look at is we're going to look at vertical projectile motion. For a lot of the grade 12s, it should be revision from grade 10 with a little bit of extra, maybe. Graphs were probably forgotten because it's been a while.
No, but it's good.
We're going to look at vertical projectile motion, equations of motion.
So if anyone has questions, they can send it through to us. We'll be here to answer questions. And Tracy, let's get down to vertical projectile motion.
Great, thank you very much.
Okay.
Well, guys, we're going to look, like I said earlier, we're going to look at vertical projectile motion. And what we need to remember, and I've sort of drawn a picture, it's just an indication, is projectile motion has three ways that we can show it. And essentially, what we're looking at is motion that's going up and down. All right, we're forgetting about horizontal now. We don't worry about that. We're looking at objects that are either going to be dropped, so we just drop them, or throw them straight down, or an object that gets thrown up, straight up and caught. Okay, or we're going to consider objects that can be thrown at an angle. Okay, now we're not concerned with what happens in the horizontal motion because that's irrelevant at this point. We're only looking at one dimension. What we need to remember, and I think this is the thing we forget, is the fact that gravity, and we remember this from grade 10, gravity is 9.8 meters per second squared. Please remember, because this is what fascinates us, is the fact that gravity always acts down. And the best way to remember that is you go, well, if you jump up, which way do you go? You end up down, okay? And if any of you don't, then I want to come live on your planet, okay? Because we know that gravity always acts down. We know that it's 9.8. Please be careful, especially if you're using old textbooks. A lot of this is the same from the old curriculum. If you're using them, they'll give you gravity as 10. We don't use it as 10 anymore. Okay, it's got to be 9.8. It messes up the calculations, but it's okay. It's more accurate. Remember, when we look at our motion, the velocity up is equal to velocity down. What this means is if I throw an object up and I catch it in exactly the same position, whatever velocity I threw it up with is the velocity I need to catch it with. Okay, it can't change. The only reason why this works is because we're ignoring friction. We're ignoring air resistance. We know that's an issue, and we also know that in reality the shape of the object, if it's a ball or a piece of paper or a feather, does play a role, but we're ignoring all of that. Otherwise the maths just gets complicated, and we don't want to do that. We're trying to get the principles in. Also, when an object gets thrown up and down, the time it takes to go up is equal to the time it takes to come back down to the ground, or wherever its starting position is. That's very important because what happens, maybe I should draw, what happens here is they'll often tell you, and we're going to look at a problem where an object gets thrown up in the air and returns to the person's hand in 2 seconds or 10 seconds or whatever the case may be, and then you go, I don't know what time is. We do. We've just got to turn it up. We've just got to halve it for going up and for coming down. This is the big, big, big thing for us, is direction. If you're using, and it's your choice, there's no set standard to this, there's nothing that says, well, down has to be positive or up has to be positive. That really is your choice. But if you choose the upward direction is positive, in other words, I throw an object up and I go, anything that goes up is positive, acceleration is negative. This is where you're going to make the biggest mistake. Acceleration must be negative then. If I choose down as positive, then my acceleration is positive, and you can't change that. This is just it's part of an exam tip. Some of you might have done this at other times, but what you need to remember is you choose the sign convention. So when you're answering the question, you're the one who decides it's got to be, I'm going to choose up as positive, down, whatever, okay? And you've got to stick to it. you're not allowed to change that halfway through your question, because then you've actually started a new set of motion, and that can't happen. Okay? Now, what does that mean for us? Well, in terms of calculations, your equations of motion still stand, and I'm hoping you recognize these, okay? So we know that final velocity Vf is equal to Vi plus A delta t. All four of these will be given on your information sheets in your exam, which is great. I just want to highlight one thing for you, because this becomes a problem. I have delta y there, and there, and there. On your information sheet, they're going to give you two sets of equations. They're going to give you Vf squared equals Vi squared plus 2A delta y, and they're going to give you one that says Vf squared plus Vi squared equals Vi squared plus 2A delta x. That delta y is important. It is displacement in the vertical direction. Okay, so be careful. In grade 10, you would have used delta x for everything. Okay, and you've used delta x last year, you did a little bit of work, you're going to do that again, where you use f delta x, I'm sure you remember that at some stage, and that was generally horizontal motion. But now, because we're looking at vertical, it's like your x and y axis in maths. Your x-axis is horizontal, your y-axis is vertical. So whenever I look at displacement, I have to use delta y, okay? All of these are still valid. But what do we need to remember? Because there's going to be certain bits of information that are just implied in the question. Like, we have an object that drops. Starts from rest, is drop, takes 10 seconds to hit the ground. And then you go, ooh, okay, I know the initial velocity is 0. I know time, but I'm given nothing else. But you're told what the acceleration is, which is 9.8. So be careful here. They're not going to tell you it accelerates due to gravity. If it's vertical motion, you're going to use 9.8. There shouldn't be any reason why you use something differently. Okay? And if it is, they need to give you enough information to do that. Okay? Now, that brings us to a fun concept called terminal velocity. Okay? Now, when we get terminal velocity, it actually only happens, we can get it in air resistance, so 9.8 is only in a vacuum, okay, or for small objects covering small distances, which is what we sort of do. But think about those people who like to jump out of aeroplanes. It's not something I want to do anytime soon.
Oh, no.
No, not at all. It doesn't really, yeah. Anyway, so they jump out of an aeroplane, and before they pull their parachutes, I'm hoping you've all seen this, they fall horizontal, and then if you actually watch them, it actually looks like they slow down. But now I'm telling you that they should be accelerating at 9.8. So what is actually happening here? Well, in the real world, we have air resistance, and air resistance pulls up on them. And what happens is, under normal circumstances, okay, we should have the weight of my person jumping out the aeroplane, or whatever object it is, which is mass times gravity. You remember that from grade 9, I hope. And then the force of the air resistance. So what happens here, and if I can get my little, I should have a mouse here. There we go. Now, what that means is when I look at the resultant force, I'm hoping you remember that, the resultant downward force is bigger than his weight. So he's going to accelerate for a little while. And so what that means is his acceleration is greater than, well, smaller than gravity, but it's still accelerating. But then there comes a time where the two forces are equal. That does happen. And what happens here, there we go. Okay, it's gone away. There we go. Your resultant force is now 0. That means, if you remember from Newton's second law, that your acceleration is 0. Force up equals force down. Very special circumstance, and they will tell you about it. And terminal velocity only happens, there's got to be a certain, you can't get terminal velocity throwing a stone off the 3rd story of your school building, so don't do it. Okay, now, Last thing we need to look at, and I'm pretty sure you're all groaning right now because now we need to look at graphs of motion. And we all hate them. I agree, but you are going to get them. Okay, they love graphs of motion, and there's certain things they're going to ask you about this. One, there's going to be interpretation. So they're going to give you a graph and they're going to say, what does it mean, calculate things, draw the graph, that sort of thing. Or they're going to give you a problem and tell you, draw the graph. Either way, okay? Now, in terms of your displacement, I've got a free-falling object, so I'm saying, well, I'm just letting an object drop, okay? When we look at the shape of the graph, now let's consider an object that I'm actually going to throw up and catch. Displacement, I'm hoping you remember, is a vector, which means displacement has direction. Okay, it's very possible for there to be a negative displacement, but if we remember from our graphs, the displacement, when we have uniform acceleration, your displacement, remember, it's getting faster and faster and faster. That means that your object is going, or slower and slower and slower, depends on direction. Your object's change in distance every second is different. So if I'm throwing an object up and down, what will happen is I get this. These are nice because it actually gives you, it looks like the shape it draws, okay? It goes up, it comes back down. Displacement is zero because it ends up in my hand again or wherever I threw it from. Distance is different, but distance can't be a straight line either. Distance is a scalar, doesn't matter about direction, but remember when we go to look at distance, as my stone or whatever it is thrown up, it goes up and it starts to slow down, then it changes direction and it speeds up and it changes the curve. So pretty much it's like taking this graph and taking the second half and putting it on top. Distance, we don't care about direction, okay? Then, what about the velocity time graph? Now this is where we all get a little shaky because we go, hang on, it's changing direction. Absolutely, there has to be a negative side to this graph without exception, okay? The nice thing is that it's constant acceleration, which means it's going to be a straight line. So depending on the values we have, we would work them out or they'd be given. And I've taken, remember I've taken up as my, should we try that again? So that it actually draws a nice line.
Sneaky board.
I love these things.
They're amazing.
You like erasers.
Hey?
Brilliant.
Incredible.
It's a good thing. I'm good at this. Yeah. Anyway, so remember I chose up as my positive direction. So as it's moving up, it gets slower and slower and slower, which is what my graph is showing. It gets to the top of its motion, which is here, changes direction and comes back down, so it's negative now. Can't be positive. But if we consider speed, speed is the same as displacement. It is a vector, the scalar, sorry, which means the speed's direction is irrelevant. So we know that when we look at it, my object gets smaller, its speed gets smaller and smaller and smaller, reaches zero, changes direction, and now, and it should be at the same gradient, and it should actually be in line with each other. So let's just try and put them together. Doesn't want to do that. There we go. What should happen, there we go. Ignore all the little dots and stuff on the side. Sorry about that. But at this middle point here, okay, where I'm just going to show you what I mean, this section here, which is now one big red dot, at that point, that's when it reached the top. It stopped. Speed cannot have a negative direction at all. That's not so bad. What about the acceleration? We've seen what happens when we get to the top of the motion, and this is the one that gets you guys every single time. We said up is positive, acceleration x down, which means acceleration is negative. Acceleration is due to gravity, never ever changes. Straight line, ooh, that is a straight line. Negative for the whole time period. It cannot change direction, okay? That was a very quick overview.
No, it was good. I've got a few questions, so that's
Excellent.
okay.
Brilliant.
Shame. Samuel, don't worry, Samuel. He says, so the graph of displacements never change. And then Lebs has said confused too.
Confused too. Okay.
So maybe they're a bit confused.
No. Okay. So if I'm understanding the question,
Yeah.
you're asking me if it's always going to be that nice curve that I showed you here.
I think
I
that's
think
what
that's
he's
what they're
asking.
asking me. Okay.
Yeah.
Not always, and it's Lebs and
This is Samuel and
Samuel.
Lebza.
And Lebza, sorry, Samuel and Lebza. This shape that I drew is for an object where I'm throwing it up and catching it again. Okay, so this one shows it's a nice direction, but let's think, and I'll just quickly do it here. What happens if, for example, it is a graph where I'm telling you I'm dropping a stone, okay? So we're gonna have our axis like we would have normally, okay? So there's our two axes, and this one is my displacement, so that's terrible.
That's a very thick pen going on there.
It is. Okay, let's just make that y. I'll change that in a second, and that's time, okay? Now what we said is we've got an object that's doing this, that's falling to the ground. Now as it falls down, it gets further and further apart. Logically, I'm hoping we all realize, well, which way do we want to make positive? Down, because that's the way it went. So we know it's going to, if this is my starting position, okay, that would be like displacement 0 at the top. It's going down and getting further away. So now we've got to think about it and go, okay, as it's coming down, is it speeding up or slowing down? I'm hoping you're screaming at the TV right now, or someone's Facebooking us and saying it's getting faster because it's accelerating, which is exactly what's happening, which means as we start, and then it gets faster and faster and faster, and then it speeds up, okay? So your graph will change shape depending on the circumstances and depending on the information you're given. But what we're looking for is that when it's accelerating, getting faster, your graph gets steeper, and when it's slowing down, the gradient gets less and less and less, okay? So it's difficult when you just got to talk about it. Often if we have values, it makes it a bit easier.
So we're going to carry on the next question, and then after that we've got a fantastic Facebook question from Mbali. And Mbali, if you're watching, Mbali Radebe, you know what the question is. It'll be up after this one. So let's take it away, Tracy. Last 30 minutes.
Excellent. Okay. Well, we're going to talk a little bit more about graphs because we realize that's definitely more the issue than the actual calculation. So what we have here is we have a very simple problem with a nice picture which makes it a bit easier that says consider a ball that falls vertically from rest for 5 seconds, okay? So they're telling you the ball falls, hits the ground, and then bounces vertically upwards, returning to its original height after 10 seconds. Now this is unusual because we're assuming no air resistance, which is great, but we're also assuming no energy loss. Now you haven't done work energy and power yet, but you will realize when you get there that there's absolutely no way that can happen. I'm sure you remember from momentum last year, we're pretty much saying this is like a collision, okay, and we're not considering energy. Now, what we're going to do with this is we're going to draw the graphs, and that's exactly what a question like this would say to you, is draw the distance graph, the velocity graph, and the acceleration graph, which we're going to do. But we can't draw those without knowing the values. Okay, so it's really important that we get the values in here. And what we're going to do is we're going to take downwards as positive. And what I've done over here, and I make my own learners do this, there are no marks for this, but I do this when I work out a problem, is I make a note for myself as to what the positive direction is. Because we tend to forget. We tend to go, I can't remember, and halfway through it changes. The reason why I've chosen down as positive, and you could have chosen up as positive, is because the easiest way to remember how to choose a direction is to go, well, what's the original direction of motion? And whatever that is, that's your positive direction. It just makes it easier, makes it then you don't have to keep remembering, am I using up as positive or down as positive? And sometimes it doesn't go in both directions. So if you always saying to yourselves, well, down's going to be positive, and then they only give you something that's going up, you're making your life difficult because then you've got all these negative values that you don't want to use. So with the information I've got, I need to know, before I can even vaguely think about doing a distance graph, I need to know how far did it fall. Now the nice thing is, it falls from rest. Rest means initial velocity is 0. They told you it takes 5 seconds to hit the ground, so I know time. And my equation should be a y there, but that was me, not an x. And I know a, okay? So that means if I look at this and I calculate, we're going to put that over there, we can calculate our values quite easily. I haven't done all the calculations because I'm pretty sure you guys can manage. Remember, and this is a very, very important point, when you substitute in a 0, so we've got 0 times 5, sometimes, especially if you look at some of the older textbooks, because this hasn't actually really changed, is they would just write delta y, well, delta x equals a half at squared. That used to be accepted, but it's not anymore, because in physical sciences, this 0 has value. It means something to us. It's not just an empty space, okay? So you have to include it, and that's across the board, okay? But just remember, and we all do this when we get all shaky in the exam, 0 times 5 is 0, okay? And then we've calculated and we get 122,5, which means that my object, if I don't kill myself on my mic, has gone down by 122,5, but then it goes, there we go, but then it goes up by 122,5 as well, okay? So this isn't just for one, this isn't the total displacement, it's just one direction, okay? But we haven't got everything we need yet, because now I've got distance, okay? Let's look at the distance graphs, let's look at those first. So that's where I get these values from. This is a sketch graph, which is what you're going to get asked to do. They're not going to ask you, hopefully, to draw a proper graph in the sense that you've got to do a nice little scale, and because that just takes far too long. But they are going to ask you to draw sketch graphs with relevant information, like I know that it's 122,5 and 245, and the time frames that we were given, okay? Now this is this first graph is distance. So we go, okay, well, what happened to my object? As it comes down, it's a lot like we did the last one, it's coming down and it's getting faster and faster and faster. So if we draw this in, it's coming down and it goes faster. Ooh, that's not going to work. I need to draw a little bit smaller than that. Let's do it in that one rather. It's getting faster and faster and faster. There we go. That's a much better line. Not even sure what I did.
It's a very good line there,
it's much
Tracy.
better, actually. You can actually see what it's doing now. Okay, but it's getting faster and faster and faster. It hits the ground, and now it's going back up. And we're going, well, acceleration is going to make it slow down. So it's going to go slower and slower and slower, and then it goes there. So it's got that nice little curve. That's because the actual direction is irrelevant. But what about the displacement? Now, all we've done with this question is instead of throwing it up and down, we've bounced it on the floor. So it stopped and started at the same place, which means this point, I'm going to need to stand here, and that point is my beginning and end point. Be careful now with the height, because it only goes to 122,5. So this is a much smaller graph, okay? Be careful here, and there must be this distinction because this has direction. So my displacement, the direction is important, very, very important, okay? Hopefully sort of making a little bit more sense for you guys. Now, the next graph is the speed and velocity graphs. Now I've already pre-prepared these, and you go, well, I only know one speed. It started from rest, which means I need to work it out. Once again, I'm only taking one direction. So when I do this one, let's just move that over there. We work it out, and this is where working with 9,8 is a real pain because we get 49. Okay, so also this is something you need to be taken into you need to take this into consideration when you're looking at old textbooks for questions, okay? Is they used to work these out with 10, so sometimes the answers don't work out so nicely anymore. And it's hard to work out questions, so they work out nicely now. All right, so we get 49, which means when it bounces on the floor, it's 49 meters per second. Speed, what does it do? Well, speed, we know it's going to be a straight line. We spoke about that earlier. And it is literally just going to go from here, and it goes up, gets to 49, and then what happens to it? Wow. Me and this board are going to have to make friends. Okay. So ignore that. Okay, you shouldn't have that. I'm so sorry. I don't have one of these in my classroom. Can you tell?
I know. I don't have one of these at home either.
I wouldn't like one of these at home.
home.
Yes, I'm a nerd. I'm a science teacher. Anyway, so speed, not concerned with direction. Velocity, we are. Now, we've chosen down as positive, which means it starts at the top. At 5 seconds, it goes through 0, and then it goes back to 10. So the nice thing is, it's a nice straight line going through the axes. Can you see the shape sort of looks the same? It just doesn't always follow. It just depends on the question. And then, because now in the last example when I showed you, I said 9,8 was negative, but we've chosen down as positive. So that means my acceleration is positive 9,8. But we needed to have the values, okay? I'm hoping that sort of cleared up some of the problems.
Guys, this is only the beginning. Tuning in from the beginning, I promise you, you're going to ace those exams. Learn more, learn extra, and thanks for joining in, and we'll see you tomorrow. Bye, guys.